Good afternoon, everyone, and welcome to the Cancer Research Institute's webinar series, Cancer Immunotherapy and You. Today's date is Wednesday, October 19th, 2016, and the title for today's webinar is New Ways Immunotherapy Targets Breast Cancer. Before we begin, I'd like to thank our very generous sponsors. This webinar series is made possible with support from Genentech and LabAnswer and its employees, and our friends at AbbVie, Celldex Therapeutics, NewLink Genetics, and Regeneron. My name is Brian Brewer, and I'm Director of Marketing and Communications at the Cancer Research Institute, a nonprofit organization dedicated to saving more lives through research that aims to harness the immune system's power to conquer all forms of cancer. We fund scientists around the world whose work has led to significant breakthroughs in cancer immunotherapy research and treatments. Over the next 45 minutes, you'll hear from an immunotherapy expert about how cancer treatment is undergoing a revolution thanks to these breakthroughs, followed by a question and answer period. Now it's my pleasure to welcome today's expert speaker. Dr. Silvia Formenti is chairman of the Department of Radiation Oncology at Weill Cornell Medicine, an associate director of the Meyer Cancer Center, and a radiation oncologist-in-chief at NewYork-Presbyterian Hospital. Much of her work today focuses on treating patients with combinations of radiotherapy and immunotherapy and understanding how the two treatment approaches can enhance one another's effectiveness and lead to better clinical outcomes for patients. Dr. Formenti, we're grateful that you could take time out of your day to join us, and welcome.
Thank you, Brian. Good afternoon. This first slide shows the proportion of Americans who are grouped based, unfortunately, on their cause of death. And the slide is trying to convey the concept that compared to the 1958-1960, some cause of death have decreased, and so people don't die anymore of those conditions. Others have not changed, and others have increased. So you can see on the bottom, Alzheimer's disease has increased because we're making a better diagnosis of Alzheimer's disease than before, and more people achieve longevity and eventually may get Alzheimer's disease. What is, however, the reason for showing you this slide is that while disease of the heart, so cardiovascular conditions, are going down, this green line here, let's see, let me just get the marker. To get the marker to move over here. I don't think, here it is. So you can see that it's going down over time. When you look at malignant neoplasm, so cancer, is pretty much flat. That to me is suggestive that the way we have gone about with cancer therapy has changed quite dramatically the quality of life and the life expectancy of people diagnosed with cancer, but has failed to cure them in a different proportion from the 60s. So still the same number of Americans end up dying of cancer compared to the 60s. So patient that was maybe diagnosed with metastatic melanoma in the 60s would have died of metastatic melanoma, but faster than a patient who is diagnosed with metastatic melanoma today, but the same proportion has remained. So it is clearly time for a paradigm shift, and that paradigm shift comes from immunotherapy. So what is cancer immunotherapy? Standard cancer therapy, whether it's chemotherapy or radiation, attack the tumor cells directly, so somehow interfere with the cell growth. But immunotherapy is a treatment that activates the immune system to fight cancer. So it's a somehow different target. So this has been successful enough to get the cover page of important journals like Nature and Science, but also the media. And in fact, is to the progress of cancer immunology that we have understood some of the mechanisms for the crosstalk of cancer and immune system, and interpreted them and tried to correct the deficiency that occur once cancer is established, and encountered the first successes, which I'm sure many of you are already aware of. So let's just go back a little bit about the basics of why the immune system is an important target in our fight against cancer. So the immune system is capable to recognize and kill cancer. So in fact, the immune system is designed to distinguish between normal and cancer cells. We are built in a way that the immune system can maintain the same normal cells. When that fails, usually is because of autoimmune diseases like lupus or other conditions, because the immune system and these immune cells that are permeating our body are capable to recognize markers on normal cells that make them safe and self and not reject them. So the immune system is capable to ignore normal cells. On the other hand, if a normal cell slowly and gradually becomes mutated, it becomes a cancer cell, it starts expressing abnormal cancer markers that the immune system is capable to recognize as foreign and dangerous. And in most of the cases, the immune system is capable to recognize these cells, these transformed cells, attack them, reject them, and eliminate them. So particularly through aging and being exposed to a lot of cancerogens, many of our cells can make these mistakes, and they are very effectively eliminated by our functioning immune system. So this is an example of a T cell that is attacking a cancer cell. This is a real cytotoxic T cells. It's a cancer cell in the middle, and you can see how here we are. You can see how engaged the two cytotoxic T cells are with the cancer cells, and eventually they will be able to create what is called as an immunological synapses, capable to release granules and kill the cancer cells. However, with the process of aging and the exposure to more and more carcinogens, eventually the immune system can fail to reject abnormal or mutated cancer cells. So in the process of attacking, either it stops too early or somehow the attack is insufficient, particularly because the cancer cells have also acquired capacity and often are embedded into a tissue, a microenvironment that may trick the immune system into making it believe is self, is not something to reject. So in that case, even if the attack exists, the cancer cells find a way to prevail and continue to establish themselves. So this is an example of, real example of a study our group conducted, whereby these panels contain images of section of breast cancers from different subset of patients. And the patients come from a cohort of 481 triple negative breast cancer patients who accrue to ECOG clinical trials. and part of the requirement of the accrual was to have a central review of their original biopsy. And the pathologists who reviewed biopsies were able to group the patients based on the amount of immune cells. Here is a patient who has no immune cells, 0%. A patient who has 20% of immune cells infiltrate. One who has, and the immune cells are those blue dots. One who has the 50%. So you see there are more and more of those tiny blue dots. And this is a very rich infiltrate of 80%. So the scope of this study was to try to assess whether, similar to colorectal cancer, breast cancer also could be classified based on the immune infiltrate. And in fact, this study demonstrated that you could break down these 481 patients into different subsets that in fact will have different infiltrate, and then try to see whether the degree of infiltration reflected on the likelihood of surviving or not from the disease. So, here we are. So here is the patients in pink on the top are the patients who had the most infiltrate, like 80%. In blue had the 50% infiltrate, in the light blue, dark blue, the 20%, and 0% were here. So the likelihood of surviving the disease depended on the original infiltrate. All these patients had the same treatments. So that predicted quite strongly, with a strong statistical association, for the likelihood of surviving disease independently from, since the treatment was the same. And the authors concluded that for every 10% increase in infiltrating lymphocytes, there was a 14% reduction of risk of recurrence of death. So what is really telling us is that for women who at the time of diagnosis, the immune system is well engaged and somehow also fighting the battle against cancer independently from our treatment, those women are much more likely to be alive. And here is showing 14 years later, so quite a long follow-up, than the patients who had zero immune response. So in evidence, the immune system is a very good alliance to have. It's also showing that, unfortunately, only a minority of women had a strong infiltrate for the time we made the diagnosis. Because if you can see on this image, you can see the evidence that the only 21 cases have the pink line, you see, while the majority of the patients had a modest or no infiltrate. So while it's nice to harness the immune system, for a time we make a diagnosis of established breast cancer, often the immune system is not available to help us fight the disease anymore. So just to repeat this concept, the immune system is present at the tumor site, but incapable of rejecting the cancer, and immune suppression dominates in established tumors. So for every 10% increase in tumor infiltrating immune cells, there is a 14% reduction of risk of recurrence or death. So maybe one option is to bring back the immune system to help us out for those patients who have a poor infiltrate or no infiltrate. And to this purpose, approximately 15 years ago, we started studying whether using radiotherapy can reset the immunological phenotype, the infiltrate in the tumor. So the idea would be that, at the beginning, before radiotherapy, there could be the majority of breast cancers I've shown you before with little tumors, present, infiltration, tumor infiltration present. Or the type of infiltrate that is not activated and is meaningless. But after you give radiation, you start sending signals and modifying the tumor to a way that can now elicit the immune system, and immune cells will come into the tumor much more freely, permeate the tumor, and eventually go to the draining lymph node where they can activate an immune response. So we started exploring this evidence and somehow pursue it preclinically in animal models and then verifying it clinically. And I'm going to show you some examples for that. So the idea is that radiation can convert a tumor from lymphocyte poor into lymphocyte rich, which is, as I shown you before, makes a tumor much more compatible with survival and a better outcome. So if radiation is capable to do so, you could start seeing something that has been extensively described in the literature, even if it is a relatively rare event, called an Oxcopal effect. So the idea will be that by treating a tumor in a metastatic setting, for instance, so this is a tumor that gets treated, but this patient has both this lesion and another lesion in her hip. So while she's getting treated to this lesion, not only you get a response in the lesion treated, but you also see a disappearance in the blue circle in the other lesion. So this is an abscopal effect, because even if the treatment was in this area, this other area goes away. Not just the treated one, but also the area that was not treated. A way to explain this out of the field effect is that by treating this lesion in the field, we elicit an immune response. So the tumor becomes like a vaccine, a local individualized vaccine for that patient. And now the immune system of this patient has learned how to reject this metastasis and applies that knowledge to reject another one. So we have, in fact, actively immunized the patient against hers or his tumors. However, abscopal cases are extremely rare. And this is a review recently published that look at the literature and demonstrated that between 1969 and 2014, only 46 cases, like the one I described you before, have been reported in the literature. So it's definitely a really rare event. Why is that? Why are abscopal effects so rare after I made the point that radiotherapy can help activate the tumor, permeate it with immune cells, and convert it into some kind of an individualized vaccine? And the reason for this limitation in abscopal effects is that for the time we have established tumors, so with the time we make the diagnosis, there is so much immune suppression that even with a good pro-immunity effect of radiotherapy, it's very difficult to overcome the blindness of the immune system. And this complicated slide, I'm going to try to very slowly dissect, shows what's going on in cancer. So you start, as I've shown you before, from a highly immunogenic transformed cell that the immune system is really capable to reject usually. But somehow, as I've shown you before, sometimes the immune system, particularly with aging and with more mutations and more difficulties in handling the challenge of rejecting so many mutated cells, the immune system is incapable to reject all mutated cells, and you start selecting for poorly immunogenic transformed cells, which are these darker ones. Here. Right? And over the course of these poorly immunogenic transformed cells escaping the immune system and continuing to grow, there continue to be some infiltration of immune cells trying to fight the tumor. But the tumor itself starts sending signals to recruit immunosuppressive immune cells. So somehow bends the immune system to allow for its growth. So somehow recruits the immune system to its own survival. And also paralyzes the capacity of this existing tumor to evoke a rejecting immune response. Eventually evolving to a situation where there are only these polyimmunogenic transformed cells, as well as other actively immune suppressive cells in brown, that use all these different mechanisms around here to sustain immune evasion. So to maintain the blindness of the host against the tumor. And this evolves to a point that at the time of metastasis, the tumor is taking over slowly and gradually vital organs, with the immune system getting more and more blind, and eventually results on the demise of the patient, kills the patient. So in the past 20 years, a lot of progress in cancer immunology have elucidated much better this mechanism, both the mechanism of limitation of an immune response by somehow modulation of antigen presentation and mediators of cell death and so on, the effect of immune checkpoint pathways like the CTLA4 or PD-1 or TGF-beta. So I'm going to show you some examples of how interfering with any of these pathways in combination with radiotherapy may result in a preclinical and a clinical response. So of course we go back and forth between testing hypotheses preclinically in mice and bring it to patients or in cell lines, and vice versa, learning from our patients and going back to the lab. So this is a classical example of translational research. So the very first experiment that substantiated what I've told you so far was to create a breast cancer mouse model, and this is an experimental animal where it grows two separate tumors on the right and on the left. We give radiation to one side, and then we look whether we have an effect not only in the irradiated one, but also in the other side of that is not receiving radiation. And if we give radiation alone, we wouldn't expect, as I told you, this Oxcopal effect, this effect outside the field is extremely rare with radiation alone. But maybe if we give radiation and some immunotherapy, we can start seeing some effect. And we decided to test in this model a drug called FLT3 ligand, which is just increasing the number of dendritic cells. There are important cells in doing antigen presentation and helping, the mechanism of rejection that I showed you, successful tumor recognition and rejection. And when we combine radiation with FLT3 ligand, we look at the response both in the tumor and in the irradiated tumor and in non-irradiated tumor. And these are curves just showing what happens in the irradiated tumor. These are in black, animals that got the same setup but no treatment, so that both tumors continue to grow, both in both sides. Both on this side and on this side in black. If you give no radiation but just the drug, the FLT3 ligand, as you can see, the tumors continue to grow, both in the irradiated side and the non-irradiated side. Now, when you give the radiation to the primary tumor only and no other treatment, the primary tumor, of course, responds to radiation because it's cytocidal. It's a treatment that kills tumor cells. But the other side does not respond. In green, continues to grow. But if you give the two together, now you start seeing not only response in the irradiated side, but now with the help of this immunotherapy, FLT3 ligand, you see the response on the other side too. And this was the first evidence that combining radiation with immunotherapy could be more effective than immunotherapy alone. As you can see, the FLT3 ligand alone in red continue to have the tumor growing in a non-irradiated site. And once you give the two together, you can see that there is a response. So we took at heart this finding, and this is just a summary. We moved from this combination in a preclinical model to a clinical trial. It was a proof of principle trial where local radiotherapy and GM-CSF, which is very similar to the FLT3 ligand, the same idea of increasing dendritic cells and cross-presentation. And then we tried to generate Oxcopal responses in patients who had heavily pretreated metastatic solid cancers, including some breast cancers. And we're very pleased to see that approximately 1 out of 3, 1 out of 4 patients had these Oxcopal responses. Responses you would have not seen just with the GM-CSF, but you could see by the combination of irradiating one lesion and giving the GM-CSF. And most importantly, you see these patients had very advanced disease compared to the patients who couldn't get a response and had only 8-month median survival, average survival. The ones who could have response had almost 3 times the survival. So we made a difference on the survival of these patients. And this is an example of a patient. These patients have to have metastatic lung cancer, but we treated this very large lesion here that in a sagittal projection, so just cutting across the patient. This is a sternum of a patient over here. Its back. You can see we treated this lesion here. Did not treat this lesion was outside the radiation field. It's the same lesion here, outside of the radiation field. And we gave both radiotherapy to this lesion and GM-CSF. And we're able to show that the lesion was not treated. So this one up here, which is based on the back, this is the spine of the patient. So this is the original lesion that was not treated by radiation, went away completely and remained controlled until for several years until the patient eventually progressed. So this first proof of principle trial gave us confidence, and we were very lucky to receive the support of Dr. Jim Allison, who is being a pioneer in a novel type of radiotherapy that removes the brake to the immune system. And he's the recipient of the 2015 Lasker Debate Clinical Medical Research Award for having elucidated the mechanism associated with blocking CTLA-4. And so Dr. Allison gave us the drugs to test this hypothesis with radiotherapy, first in a mouse model. And the basic idea is that when a tumor cell engages with the immune cells, a T cell, this is a T cell receptor up here that creates engagement, an immunological synapsis is called, so the linkage. And then here there is a brake. And if this brake is switched on, the engagement cannot occur. And one good idea was not only to facilitate the engagement, but also to remove the brake. And Dr. Allison was capable to target this mechanism below here, remove the brake, and demonstrated that this immunotherapy is quite effective in diseases like melanoma, renal cell carcinoma, and so on. So we took this evidence and tested it in combination with radiotherapy. And we showed that those kind of breaks are called immune checkpoints. So if we block the immune checkpoints by using antibodies against these breaks in T cells, we can in fact activate them and enable immune specific cell killing of cancer cells. So we were able to show in mice first that radiotherapy and immune checkpoint blockade complement each other and increase each other's effect, very similar to the other immunotherapy with FLT3 ligand I showed you before. And we we're able to show that only mice that received the two, both the immune checkpoint blockade and radiotherapy, we could enhance the survival from the experimental cancer they had. And this enhancement was due to a T-cell mediated control of the irradiated tumor and the metastasis. And then we went to the clinic and confirmed that in the clinic. So this is a patient who has a very advanced metastatic non-small cell lung cancer that has grown to the liver. And you can see the liver lesions over here and the bones, and see whether I can have multiple, yeah. In the chest, all of these blue arrow signal where the metastases are. The liver has many metastases, these black dots. These larger black areas are bowel, but behind the bowel here, there is a bone metastasis, so he has disease metastatizing to the lung, to the bones, and to the liver. And this patient had undergone several lines of chemotherapy and radiotherapy, and his disease was escaping the control of either modality. So we were able to irradiate one lesion, just one small liver lesion over here, and leave all the other lesions alone and treat these patients with anti-CTLA-4. So please notice that anti-CTLA-4 alone has very modest response, almost no response in this disease. This is not melanoma. This is non-small cell lung cancer. And while you may have heard that anti-PD-1 gets responses in non-small cell lung cancer, anti-CTLA-4 has not shown much of a response pattern by itself in non-small cell lung cancer. So we treated with a combination of radiation anti-CTLA-4, and the patient got a dramatic response. And just irradiating one single lesion over here, everything went away. And most importantly, this is a patient 4 years later, still in complete remission, and we didn't give him any other treatment. So after he got 4 cycles of immunotherapy with anti-CTLA-4 and radiotherapy, he got no other therapy and no evidence of disease. So he's holding on his own through his own immune system, demonstrating that we have immunized him against his own tumor. This is another example of a lady with, this time is breast cancer. This is a lady who had a metastatic breast cancer with a large involvement. Her chest wall is not really visible here on the PET CT, but this is what we had to target with the radiation field because she had chest wall recurrences and beginning of metastasis in her liver and bone metastasis of her breast cancer. Initially, she received radiation with a different type of immunotherapy that, again, imiquimod is a cream that stimulates the immune system and particularly tricks the immune system to believe that it's like an infection. It's like very similar to a toll-like receptor agonist. So it is, eliciting an inflammation and immune response similar to an infection. So we treated the chest wall, and then we also retreated these patients. She started having a little bit of response, but some inflammation in the liver lesions and new liver lesions also coming up. Something can happen with immunotherapy that it seems like a pseudo progression. So we treated again another liver lesion like the patient before. In this case, the lesion is up here. And also gave another drug, low-dose cyclophosphamide, which is a chemotherapy agent that when used at low dose can very nicely control the immune, remove some regulatory T cells and have an effect on the immune system. And then she started getting some response, but then we moved her to a chemotherapy with anti-PD-1. And she got into complete remission and held this complete remission for a long time. So again, an evidence that together radiation immunotherapy and different forms of immunotherapy can bring a patient into remission, even in breast cancer, which is pretty immune resistant form of cancer, solid tumor. So the idea is that radiation functions to perturb the tumor and convert it into non-self. So it elicits a permeation of the immune system by sending immune stimulatory signals. It overcomes the immune suppressive signals that already exist in the microenvironment, induces what is called DC dendritic cells activation and cross-presentation in the draining lymph nodes that are draining the area that gets irradiated. That elicits an immune response by priming naive T cells, and also creates enough of a memory to then move to the next step, which is to not only to send those now tumor-specific activated T cells to contribute to the response in the field of radiation, so the original tumor that was irradiated, but now all these T cells go around like soldiers scavenging for unirradiated distant sites of disease and trying to kill those areas. And if successful, you start seeing these Oxcopal effects and somehow the demonstration that you have immunized the patient against his or her own tumor. So in summary, cancer cells killed by metastatic spread. Cancer is the result of a failure of the immune system to reject it. Cancer often blinds the immune system. Radiation therapy can unblind the immune system and restore an immune response. Radiation and checkpoint blockades or other immunotherapies can lead to tumor rejection in patients with metastatic disease. And in fact, radiation is a new class of immunotherapy. So I will stop here and entertain your questions.
Thank you so much for that, Dr. Formenti. I love how you closed out by kind of turning the idea that radiation is something that's harmful for the immune system into something that actually benefits patients who are treated when in combination with immunotherapies. I'd like to just, before we get into the question and answer phase, we only have about 8 minutes left. If you have any questions and you're watching live, there is a Q&A box on your screen. You can type into that and we'll try to get to as many questions as we can in the short amount of time that we have. Also, please know that this webinar is being recorded and will be made available on the Cancer Research Institute website at cancerresearch.org. So, first question, getting back to the harmfulness of radiation. Often patients think that getting radiation therapy is going to hurt their immune system, but what you're talking about is different. And you can see that with, in the cases of the people who have all the metastatic disease in many locations, perhaps it's not feasible to try to irradiate every single one of those lesions. And that may not actually be good for the patient, but only having to irradiate one and then giving in combination with immunotherapy, I think is a great way to demonstrate the combination of a local therapy with a systemic therapy and how the two of those things work together.
So if you give total body radiation, in fact, you can ablate the immune system by targeting the entire body. So you're not only killing the circulating lymphocytes, but also the marrow that generates these important cells. And total body radiotherapy is used for instance, for bone marrow transplant to remove the immune system of the patient to receive the bone marrow from a donor that otherwise they would reject a non-self donor of the bone marrow. So total body is definitely immune suppressive. Very large fields of radiation are also immune suppressive, but when it's targeted to a small field, radiation is not immune suppressive. And most importantly, if it's delivered in few fractions instead of the protracted classical 6-8 weeks of radiotherapy, you avoid immune suppression. So it's a different use of an established modality. It has to be tailored to make radiation really an adjuvant to immunotherapy, more than vice versa, than immunotherapy becoming a help for radiation.
You showed us those slides of tumor infiltrating lymphocytes. So and showed us that patients who had increased levels of infiltrating immune cells tended to do better. I'm wondering, is there any connection between the type of breast cancer someone has and the level of T cell infiltration? For instance, triple negative or ER positive, anything like that?
So the evidence we have is that, in fact, the slides I've shown were only from triple negative patients. The immune infiltrate is less frequent in ER, PR positive, so estrogen and progesterone positive breast cancer. But there are some cases where in the specimen, even in estrogen and progesterone positive cancers, you see quite a bit of an immune infiltrate. But it's more of a property of triple negative patients, and that is why triple negative patients are being investigated with clinical trials of immunotherapy in this moment, because probably they are the best candidates to undergo immunotherapy.
So triple negative breast cancer patients tend to do better or make better recipients of immunotherapy. Is there anything being done to look into the other types of breast cancer, and are there any immunotherapies that are being tested in those populations?
Yes, there are, and there are at least, if you go online to clinicaltrial.gov, there are clinical trials of therapeutic vaccines for breast cancer that target, for instance, HER2/neu, not only in patients who overexpress HER2/neu, but also in patients who are mild or low expressors of HER2/neu. And they are under investigation because the idea is that you start targeting HER2/neu, and through bringing the immune system to the tumor, maybe you can have enough cell death to get a mechanism called antigenic spread. So you could elicit more immune response to other parts of the tumor that are not targeted directly from the vaccine.
We have a question live, submitted live from an audience member, asking if circulating tumor DNA could be used to identify which patients might respond to immune blockade or other immunotherapies. Are there any biomarkers aside from looking directly at tissue samples to see the level of T cell infiltrate, are there any other biomarkers that doctors are looking for to see whether a patient may or may not respond to immunotherapy?
Sure, there are a big effort to try to predict which patient is responding to immunotherapy. Most of these efforts actually not going on in breast cancer, but mostly in melanoma versus non-small cell lung cancer. And one marker that has panned out is the extent of mutations the tumor has, so the mutational load, probably suggesting like a correlate for immunogenicity of that tumor. The idea of looking at circulating DNA is quite intriguing. Probably more research is going on in looking at what is the profile of circulating T cells in a way of measuring whether after immunotherapy you somehow can measure in the blood the shift toward, so the change toward a more clonal response, so a more selective cancer-specific response to the tumor compared to the garden variety of all the possible T cells with different T cell receptors for antigens, for proteins that are eliciting the immune system that we usually carry in our blood. So if we are immunizing somebody, we should see a much more specific and clonal, identical, groups of T cells in population of T cells in the blood. So that can be followed, and ideally, through a very sophisticated technology, you may even be able to select which antigens are T cells directed to. And one other information is whether the tumor has what is called microsatellite instability. Has not panned out to my knowledge for breast cancer, but is interesting, for instance, in some colorectal cancers, and suggesting that those tumors may more likely respond to immune checkpoint blockade. So we're desperately trying to figure out, before subjecting the patients to the treatment, who are the patients more likely to respond. One advantage of including radiotherapy, immunotherapy, that may be by adding radiotherapy as an adjuvant, so an additional help to immunotherapy, you may recruit more responders to that immunotherapy, the way we showed for the anti-CTLA-4 example I showed you. So a drug that doesn't work alone, but when you add radiotherapy, you make that work, you reposition the drug to work.
You showed us a slide of Dr. Jim Allison, who's also director of our Scientific Advisory Council, and I've often heard him say that chemotherapy could be considered a kind of vaccine. And so it was interesting that you feel the same way about radiotherapy, and it certainly looks like the research is bearing that idea out. So that's a good spin on things. Unfortunately, we are out of time. Dr. Formenti, I know that you've got to run, you've got patients to see. So I'd like to just close up with a few bits of housekeeping. Again, I'd like to thank our generous sponsors, Genentech and LabAnswer and its employees, as well as the following. There was a lot of information that we learned about today. If you'd like to get some another introduction that you can browse on your own time, you can visit our patient and caregiver website at theanswertocancer.org. There's information on general immunotherapy as well as a list of immunotherapies now in clinical trials for breast cancer. Lastly, I'd like to invite you all to register for our upcoming webinar on lung cancer immunotherapy, which will take place next month. You can find our registration for that very soon by coming to cancerresearch.org/webinars. Dr. Formenti, thank you so much for your time, and thank you all for watching, and goodbye.